Yeah, we got a couple more lectures to go. And I'm using them to fill in well, a couple of new topics that are interesting applications in PDEs involving reaction diffusion equations, but also to I don't know, use them as examples for some techniques and ideas that you might see down the road. I'm going to finish off the discussion of the traveling wave in Fisher's equation today. So traveling waves, that's an interesting idea that can give you insight into the behavior of a system. And then we're going to go on to the Allen-Cahn equation, which has a gradient flow structure. So that's a kind of another new idea to think of. And then from that, there's an idea in PDE analysis of energy estimates. And this is mathematical energy, not necessarily physical energy that we're talking about. These are a priori estimates of some aspects of the solution, which you can work out for general solutions without actually having to know what the solution is. You can still know something about it. This is like the maximum principle for the heat equation. So we knew something about the solution of the heat equation in certain circumstances without necessarily knowing what the solution was. And even that property gave us some insight into the behavior and let's say the correctness of the model for that application. Okay, so I'm going to go to other Brian. And make my screen smaller on real Brian so I can see the Slack channel in case you've got comments that I miss. Okay, so we were starting to talk about the traveling wave for the Fisher KPP equation. This comes up in a number of applications, but I'll say population dynamics. So remember, this was so this is Fisher KPP equation. KPP are the three Eastern European mathematicians that discovered it independently. So this was the local population growth. And this was population redistribution by diffusion. Okay, and we were looking at a traveling wave for this problem, which looked like this, right? So we were wondering whether, right? You know that if you start with non-negative, or yeah, if you start with positive initial conditions without the diffusion term, then you always tend to the stable equilibrium of 1. This is a scaled problem. And so you're thinking, hey, I've introduced some new species and it's had time back here, right? It's had time back here to grow to a population that's asymptotically tending to 1. But I've introduced it into an environment where there was none of it initially, right? So I got tending to 0 amount of the species out this way. And I'm thinking, hey, I should be able to, or I could be able to, right, find a solution which moves in time at speed c. that keeps the same shape, right? And so if it moves at this constant speed and keeps its shape, that's the definition of a traveling wave. So we'd started on our path to investigate whether such a thing existed. And so we were looking for a function that is just a function of one variable, that's this profile. And then u of x and t would be this profile moving at speed c. And we ended up with the ordinary differential equation. Right, this is this reaction term that doesn't change, right? Okay, and it's like a boundary value problem, but not on a finite interval, because I want to find a solution like this with u going to 1 as I go to the, you know, I have trouble with right and left, to the left, right? And u going to 0 as c goes to plus infinity. Okay, and last time we linearized the equations around plus and minus infinity. And we got at plus infinity, we found that u should behave something like 1 plus some constant now, which in the notes I used c over and over again, and c is already the wave speed, so we're in trouble. So I think, as I wrote last time, I think I changed this to d e to the r1 c, where this r1 from a auxiliary equation, because it was just a constant coefficient second order ODE, which we know how to solve. Put in e to the r c in this case and solve a quadratic, and the quadratic was this. Okay, and then as I went to sorry, this is the one for minus infinity, right? Because it's got the 1, right? And as I go to plus infinity, I have u is approximately equal to plus infinity, it's going to 0. So now I've got another constant, e to the r0 c. I put the subscript 0 for when the solution is near 0 and 1 for when the solution is near 1. And this root was minus c over 2 plus the square root of c squared over 4 minus 1. Right? And from the beginning, I had said you only find, you know, relevant solutions when c is bigger than 2, right? And so here's where you see it, right? If c is less than 2, right, then this has gone imaginary, which means that as I'm looking at the solution out here, right, as it's going to 0, it's got to oscillate, right? And as soon as you have a solution that's oscillating, then it will have negative values and it will be unphysical. So c less than 2, this would be oscillations around 0. These are unphysical, right? Because u would have to be less than 0, right? Some places. So now we know that we have to be looking for c bigger than or equal to 2 when we're looking for traveling waves, right? So a lot of systems have only one value of speed, right, for a particular set of parameters. This one's a little bit different, and I'll talk a little bit about some of the subtleties of the analysis that come after Math400, right, in this particular case. Here, there's still a restriction. You can't find a traveling wave at any speed, but you can find them in a range of speeds. Okay, and to actually show that for c bigger than or equal to 2, there is a traveling wave, this is when we turned to the phase plane. So we introduced w is equal to u prime. This is the game you also have to play if you want to solve second order differential equations, ordinary differential equations with numerical methods. You have to turn them into a first order system. And so my first order system will be this. My w prime, that's u double prime, that will be minus c times w minus w, oh, sorry, minus u times 1 minus u. Right, so this thing is always the same if you've converted it from a second order equation to a first order system. And then this one will be the second order equation written as a first order system using w is the first derivative. Right, and why I'm calling this the phase plane is that this is an autonomous system, right? So this right-hand side does not depend on time. So we can put the right-hand side is telling you the direction that u and w move in the c variable. Think of it as time, right? And so because the direction that they move in doesn't depend on time, we can plot that in a UW coordinate system with little arrows, right? And then we can get insight into how the solutions behave. We'll call them trajectories in this particular type of analysis in the phase plane. The solutions are called trajectories. We can get insight into how they behave by looking at how the arrows go. Now, you know you've lost something, and what you lose is you will know how the trajectories move in the UW plane, right? But you don't know the time at which they are at a particular location. That's something you would have to post-process or do numerical calculations for or something. So let's have a look in this UW plane. Right? And let's go back to the solution we're looking for, right? I'm looking for this traveling wave solution, right? Right, and I want it to, this is going in increasing c as I go from left to right. And so the solution is going from 1 to 0. And it's decreasing in u, which means that I'm looking for u in here. And I'm looking for a w negative. So the traveling wave solution I'm looking for is sitting here, right? I know I have two equilibrium points, right? Right? If I have u equals 1 and w equals 0, right? Okay, that's an equilibrium point, right? This was the, okay, hang on. This is the C going to minus infinity. I should be tending to that point. And over here, I have an equilibrium point, right? That's the C goes to infinity point, okay? So I got those two equilibrium points, and I'm looking for a trajectory that goes from this one at minus C, this one, right? Minus C is minus infinity. I want to go from there to C is plus infinity here. Remember, I don't actually get to know exactly what C is on the trajectories, because that's something I don't get from phase plane analysis, but at least I can sort of see what's going on. And I could look at the linearized behavior of the system around those equilibrium points, but I've already done it, right? I've already looked at the linearization of the problem, but written as a second order ODE, so I don't have to do that again. And here, I found that there were two negative eigenvalues of the linearization, right? And that's good, because as C goes to infinity, I want to tend to this point. I want to decay exponentially to that point, right? So this was a stable node. That's the two negative eigenvalues. I know that I'm going to tend towards this solution along the direction that is the least unstable, so the one that decays the slowest. And so that was direction 1R0, right? And here, this was a point that had a positive eigenvalue and a negative eigenvalue, so that makes this a saddle equilibrium. I want to be on the direction where I have exponential decay as C goes to minus infinity, right? Which means I want this, where did it go? I want this behavior, right? This behavior here, which in this thing means I've got a direction of minus 1R1 is the direction I want to have, right? And I'm hoping, right, that I can find a solution that looks like this. This would be the traveling wave. So you got to kind of wrap your head around this if you're not phase plane gurus, right? But this is the picture now that you want to show, right? Okay, let's just think about this for a minute, right? So if I could find a path like this that followed all of the arrows, right, in this thing, then as C went to minus infinity, I would tend to this point. And as C went to positive infinity, I would go to that point. I would be between 0 and 1, and I would have the derivative of W or of U would be negative. So that if there was a solution like that, right, then that would be a traveling wave. So here's how it works, okay? So what you do is you draw a triangle like this. Like this is not an argument that works in every case. Like this is a hand-picked argument for this particular problem to show that that a traveling wave exists for this for any C bigger than 2. Right? Now what I'm going to do, right, is I've got 3 sides of the triangle here. Right? And what I'm going to show are that the trajectories enter the triangle on all sides. Right? So this red line, I've worked out by linearization. I know this is the way it's going to behave over here. So I'm going to start here, right, at minus infinity. I know I have to come in this way, right? And then the argument goes, as c goes to infinity, I have to go to some place. The only place I can go to is an equilibrium. This is the only other equilibrium over here at the origin. So I have to go there, right? That's how this argument works, right? This is all because I've moved into the triangle. I can't move out of the triangle. So as c goes to infinity, I got to go somewhere, right? And the only place for me to go is this other equilibrium point, 0, 0. Okay, so let's see how that goes. We can go side by side. So let's look at side number 1. That is where w is equal to 0, and u is between 0 and 1. Now, I'm interested to show that all the arrows go in, so I want to show that w prime is negative. Well, I just look over here, and when w is 0, I get minus u times 1 minus u, right? That's negative. So now I know I've got these arrows are going in. Okay, one side done. There's 2 easy sides and then one where you have to do a little bit of work. Let's look at this side. This is where u is equal to 1. Here I want to show that what do I want to show here? I want to show that I've got here that I'm showing that w prime is negative, but I don't think I want that, right? Here I've got u is equal to 1, and I want to look at, I want u prime to be negative. Okay, so let's look at u prime. It's w, and that's less than 0 on this side. Okay, so there was a problem with the argument in the posted notes, and I just fixed it. Luckily, it was a trivial problem, because you know I don't do well fixing things as I lecture. Okay, so that's good. This one is a little bit trickier, this third side. Just to make the algebra a little easier, I'm thinking of taking what I'm calling b there to be a positive number, right? So, okay, so it's down here, right? It represents a negative value of w, but I'm just thinking of it as a positive number. So this point is actually the point 1 minus b, okay? Okay, and I'm going to look on the line. That's number 3 line. I'm going to have a normal direction. This is easy to work out. A normal direction is going to be B1. Here I am on this line. Here's this normal direction, B1. So now you can see that this is the right picture when I take B to be a positive number. And on the line also, the value of W is minus B times U, right? It's just this is just a straight line. W is minus B times U. So I want to look at the trajectory direction. D. That's the right-hand side of the ODE. I want to look at that on this line with W is minus B times U. Well, U prime is W, so if W is minus B times U, then I get minus B times U, right? And the other right-hand side is this one, and if W is minus B times U, then this is CB u, and then I've got minus u plus u squared. Well, and this is the picture I want, right? That D points inside of the triangle, right? And that will be true that the trajectories point inwards. We need to show that the dot product of those two vectors is positive, right? And it's got to be true. It's got to be positive for all u between 0 and 1, right? So we need to show that n dot d is bigger than 0. That's inwards. Okay, so there's a little bit of math 221, 152 coming up here, right? So I'm going to do n dot d. Okay, and okay, there's some algebra which shows that this is got to be bigger than minus b minus c over 2 plus c squared over 4 minus 1 times u, which is positive. And this is bigger than or equal to 0 if if you take b as c over 2, right, then this thing is 0. And then we get our condition that c has to be bigger than 2 again. Okay. So, okay, I'm not sure how much phase plane analysis you get in previous ODE courses, but this is either a reminder or a taste. And it's exactly the kind of theory you need to show that a traveling wave exists for this particular problem. So, a traveling wave exists for every c bigger than or equal to 2. Okay, so now something really interesting comes up, which is past Math 400. So I've got in the notes, I'll just reproduce it, some quite deep theory. This is typically not even done in a first graduate course in PDE, but a later graduate course that will show that these waves, these traveling waves, are stable. Okay, and why this is deep is actually defining stability of traveling waves is not so straightforward, right? And there's different definitions which you have to think very hard about which one would apply to your physical situation. Okay, but more than that, I'll say some even deeper theory shows that if your initial conditions have compact support. So what is compact support? That is that u0 is 0 outside a finite interval. Then c equals 2 is the wave that results. So if you start off with something that doesn't have a long tail, right? So it's a finite disturbance, then it's the c equals 2 wave that comes out, even though all the other ones are stable. Now, I can just give you a little bit. Okay, so there's a question like a square wave. No, the c equals 2 wave is got you know, a profile that looks something like this, right? The one thing I can say which gives you a hint, and this is not like all of the technical details, it's looking at the behavior as c goes to plus infinity of the traveling wave. Okay, so did I get the sign of that right? Yes, I did. Right. As you look at higher and higher speeds, okay, let me do it in a different color, right? As c gets larger, right, then R0 tends to 0, always negative, right? But it tends to 0. And so what that means is if you have a large C, right, then you have to have a big, slowly decaying exponential solution out to infinity, right? And so this is somehow giving you the hint that to have this wave move faster, you have to sort of have preceded out at infinity some fat tail, exponential tail of the population. Whereas if you start with something that has no tail out at infinity, right, then it picks out the one that moves the slowest, the c equals 2 traveling wave. Anyway, I think this is all quite interesting. I'm not sure that there's any course at UBC that goes through those details, but if you're really keen and you're willing to learn some additional PDE, you can find research articles online. Okay, I'm going to move on to the next topic. I'll stop now and ask if there's any questions. Okay, so let's move on to our next sort of generic. Oh, there's a question. Sorry to backtrack, but could you explain how you got the result of the dot product? So I'm not sure what you're asking. This is the.
I can just talk and explain how I'm confused. So I know how dot product works, but I'm just kind of confused at how you ended up with like the b minus c over 2. I worked it out myself, but I'm not sure if that was just factoring or if you put the R1 and R0 back into there. And I was just wondering if you could explain that, if it was just factoring or if there was something with the roots, so I know what to do in the future.
It's just factoring. Okay, so I just took this, right, and I take the dot product, I get, here, let me do another color, I get a minus b u minus b squared u, right? So that's a term I don't like, right? Because I want to show something is positive. Now I'm going with this 1 times this thing, so I get a CBU, and then a minus u and a plus u squared, right? So if I cross this off, right, because that just makes it more positive, then I get this thing. So that's where it goes, right? So this is the minus b minus c over 2 squared times, and it's all times u, right? Now you notice. And then I get the minus 1, and then I have to complete the square. I get the plus c squared over 4. Okay, those details are a little expanded out in the notes, but does that make sense? Okay, good, good. Yeah, it's the sort of thing I could easily make an algebra error on, but it looks okay, even having done it a second time. Although, of course, the problem is sometimes you make the same mistake over and over again as you try and reproduce your calculation. Okay, quickly, let's go on to the other generic reaction diffusion problem, scalar problem, the Allen-Cahn equation. Right, so here I'm going to have ut is uxx minus f of u. And the reaction term here is, it's got an epsilon in it. You can scale it out, okay, if you're willing to scale space, but this is something which I'm going to leave in because it's interesting in later discussions. Okay, so this is 1 over epsilon squared u times u plus 1 times u minus 1. Okay, I talk about generic, right? Well, so Fisher's equation was the generic one that had 2 equilibria, right? One stable and one unstable, right? And this one is got 3 equilibria, right? 2 stable, 1 unstable. So this is how you get it. And of course, we're not going to worry about boundary conditions, but I'll say this is the Cauchy problem. So that's, you're going to get a u0 of x given for all x. So no boundary conditions because we don't want to worry about those. So just like we did for the Fisher's equation, let's forget diffusion for a minute and just look at the reaction term. So if I had u dot is minus f of u, right? We've got this number line with arrows on it. I'm going to have f of u, and of course now I have to remember that my arrows aren't going to have the sign of f, they'll have the opposite sign because I got the minus sign. I mean, that's a bit of a pain, but that's just how this equation is typically written. Right, so I've got equilibria at 0, 1, and minus 1. Right, and if I draw f of u, I get a cubic, looks like this. Right, and if I draw the arrows, remembering to change the sign, right, f is negative here, so I've got positive arrows here, I got arrows this way, and then I've got arrows this way, and I've got arrows this way. And so from here, I can see that these guys are stable. And this guy's unstable. Okay, and this is a model of, it's a material science model. And it is a model where you have crystal grains of different orientation, and they can be mixed, right? This is a continuum model. So when you talk about u is equal to 0, then you have some kind of mixture of the crystal orientations locally is half and half, right? And over here, you've got all one orientation, and over here, you've got all the other orientation. And this problem's a little bit artificial in 1D. I'll talk a little bit about 2D and higher later on. Okay, and so now what we can do is add the diffusion term back in. Okay, and if you think about it, right, this reaction term is scaled to be really big, right? Because whenever you see an epsilon, you should usually, in applied math, you should usually think of it as being a small positive parameter, right? So epsilon going to 0 means the reaction term is really big. Diffusion is small, right? And so what's going to happen is, very quickly, you're going to move to regions that are either +1 or -1. And then diffusion only kicks in because, right, then you're going to have large second derivatives between the regions of +1 and -1. And those are going to be described by a mix of the diffusion and the reaction term. Now, I'm going to say you could, because we just looked at the Fisher equation, there was a traveling wave. You could look for a traveling wave solution, but there aren't any. Okay, so no traveling waves. And when I show you something later on about the structure of the dynamics, then you'll understand why there can't be any traveling waves for this problem. So there's no traveling waves, but there is a steady state solution. Right, and this is like an analytic form. It's the hyperbolic tangent of x minus x0. So this is like just this is a parameter, right, in the family of steady states over 2 epsilon. Right, and you can see where the scaling of space by epsilon comes from. Right, you have to have a competition between these two terms. Right, f is already size 1 over epsilon squared. And so if you want the second derivative to be also of size 1 over epsilon squared, then you really expect this kind of scaling in the solution. Now, this is not an asymptotic solution. This is an actual solution, right? This is something you can, just by chance, you can find an analytic formula for. And so what does this look like? This looks like one of those transition layers that I talked about between one state and another. And there's a question that came up in the chat, which I'll be able to address in just a second, right? Just like the traveling wave solution. Okay, so I'm drawing a pretty terrible hyperbolic tangent, right? So this is u of x steady state. Right, so once you find a solution that's hyperbolic tangent of x over the square root of 2 or over 2 epsilon, then you can, there's no x's in this equation, right? No x's, no t's in f, right? So it's autonomous. And so once you find a steady state solution, you can just move it, you can just translate it around. It'll still be a solution, right? So the x is just the location of the 0 in a steady state solution that can exist, right? And then I'll just say that the width of this thing is O of epsilon. Now I'm wondering if you guys have seen this notation yet. This big O, right? This is big O notation. So an O of epsilon term, this is just a quantity that is approximately equal to some constant times epsilon, right? And if you've got an O of epsilon squared, right, that means it's a quantity that's like a constant times epsilon squared, right? So this is just like a rough scaling thing. When you see big O, it's just saying, hey, I've got a parameter and it could be big, it could be small, and I'm interested in how some other quantities behave on it, okay? I've tried to think back and figure out whether we had introduced this big O notation in the class previously. Of course, you might have seen it in other classes. So let me tell you a little bit about how things behave in the dynamics. So if you start from general initial conditions, right, then what happens is you will quickly tend to regions of u approximately equal to either plus or minus 1, and they'll be separated by diffuse interfaces of width O of epsilon. And quite quickly, those regions will, those diffuse interfaces will take approximately this hyperbolic tangent shape, right? So I'm going to take things are typically done with no flux boundary conditions. So homogeneous Neumann conditions. I talked about everything as a Cauchy problem, but let me change my mind a little bit here. So you're going to have, you know, a region where u is approximately equal to 1. Some other regions where u is approximately equal to minus 1. Are you guys still seeing the screen? I don't know what happened there. Okay, okay, I got a thumbs up. Okay, and then you'll have these smooth interfaces that go between these things. And there's some fun math associated with these things. The 1D problem's a little bit artificial, but that doesn't mean you can't have some fun math with these things. And these are approximately the these hyperbolic tangent profiles scaled by epsilon, and they will move. So the interfaces will then move, but they move very slowly. So it's, I'll say, exponentially slowly. So they're like the time scale is like order e to the minus c over epsilon. Okay, so they actually like it's really slow motion. Okay, and then in this case, in a bounded interval where you put these boundary conditions, homogeneous Neumann conditions, then the actual steady state is either u all 1 or all minus 1, right? And this is where you can sort of see, right? You've got these crystal orientations, right? They're competing one another. It's in an annealing process. And one of them will eventually take over the other one, and you'll have all uniform crystal. This is annealing to infinity, if you know what I mean. In higher dimensions, things are a little bit more interesting. Then you have solutions where you have interfaces, right? But they're not straight interfaces, right? So you're going to have u approximately equal to plus 1 and u approximately equal to minus 1. And you can talk about an interface, but it's not an exact interface, right? It's going to be this smooth to diffuse interface that's got the width that's order epsilon. And if I looked at a normal coordinate through the interface, right, then I would have u is approximately equal to the hyperbolic tangent of that normal direction divided by 2 epsilon, right? And these interfaces also move, right? But in the 2D case, these interfaces move in O of 1 time, and they move with curvature motion. So, or mean curvature motion in 3D. So, right, you can sort of see that this thing is curved this way, and so this interface would move with normal velocity equal to the curvature. So you end up with some free boundary value problems in the limit, but they're different from the free boundary value problems that we found before because the entire problem lives on the interface, right? You just need to know the interface to work out the curvature and then work out how it moves. And there's some pretty interesting numerical methods for computing curvature motion. Okay, so I've got some computations I can show you of the Allen-Cahn dynamics in 1D and 2D. But before that, I want to do a little bit of this stuff I talked about, this energy estimate stuff. Okay, and what I'm going to show you now is the thing that will convince you that there can't be a traveling wave solution. So Allen-Cahn is a gradient flow. On the energy, which is, right, if you give me a function u of x, right, then I can work out the energy associated with that thing, right? It's got something associated with the interface, and then it's got some chemical energy. Right, okay, and this W of u is 1/4 u minus 1 squared times u plus 1 squared. And if you work out the details, we'll need this later. If you take its derivative, you get the f of u, the u cubed minus u term, okay? So if you're going to talk about the physics of this energy, right, this is the interfacial energy. And this is the chemical energy. Right, this W of u is just a double well that looks like this. So in terms of the chemical energy, right, if you are in a gradient flow of this energy, you're trying to get to the energy minima. So this is saying I want to get to, okay, sorry, there's a bee buzzing around my office. I'm going to open up the window and hope it goes out. It's one of those giant bumblebees. It's very noisy. And I also want that bee to live. I don't want it to die trapped in my office. So hopefully it'll leave. Okay, so right, the dynamics want to decrease the energy. We haven't seen that yet, but I'll show it to you, right? And so it wants to end up in one of these wells, right? Because that's where the energy is the lowest, right? In either, you know, one phase or the other, right? But if you have a mix of -1 and +1, right, then you get penalized, right? Because you have to have some of this stuff between the two groups. And it really doesn't want that either, right? So this is something that something which I'll show you the dynamics that the dynamics minimize. This is an energy that's specific to the Allen-Cahn equations, right? I mean, you can have any function of x that you want and put it in this expression, right? But it's only relevant to the Allen-Cahn equations and some other equations as well, but specific ones. So now I'm going to consider u of x and t as a solution of the Allen-Cahn equation, right? And so now I can look at this thing, right? I'm putting the dot in here because I'm not just putting a value of u at 1x. I'm putting the whole function of x at a given time, I'm putting into E. So I'm going to put that into, I'm going to look at this energy at that time for the function of x. Right? So this is this thing up here. And now I'm going to look at how that changes in time. Right? This E is just a scalar, right? It's just a number, right? It's a positive number. And I'm going to show that it has to decrease in time. And in a particular way, which you can identify as a gradient flow. Right? Well, okay, so let's take the integral. If I'm going to take the time derivative of this integral, I have to take the partial derivative of all the stuff inside. So this is going to be uxt, right? And then I'm going to have to take the derivative of w with respect to u with respect to time. So this is going to be w prime of u times ut. Right? And here, I'm going to integrate by parts. And I'm going to assume that ux goes to 0 at x equals plus or minus infinity. And if this was a bounded domain, right, then I would have these boundary conditions on the boundaries. Okay, so that means I can take the x derivative and I can move it over there, right, and change the sign, right? So this is now the integral from minus infinity to infinity. Now I've got minus uxx plus w prime of u, and it's all multiplying ut, right? Once I take the x derivative over there, then I've got ut. Right, and now let's look at what ut is, right? That was uxx minus f of u, right? So that's uxx minus w prime of u. So this is now a u minus uxx plus w prime of u times uxx minus w prime of u. Okay, oh, and this is all integrating in x. So this is minus the integral from minus infinity to infinity, uxx minus f of u squared dx, which is less than or equal to 0. So if you follow this quantity energy on solutions of Allen-Cahn equation, then this energy has to decrease. So that's interesting, right? So this is now an a priori bound on the behavior of the solution. If you put in your initial conditions, right, then you're going to get a value of this energy at time 0. And you know, without knowing all the details of the solution, but that this quantity has got to be smaller than that for all later times, right? And so there's some analysis you can do, existence and uniqueness kind of analysis with those kind of estimates. Have people seen gradient flows before? Gradient flows, okay, a little, okay, there's only one person that I can see on the screen, or two. So let me tell you, let me remind you or let you know a little bit about what these things look like in the finite dimensional case. So this is an infinite dimensional version of finite dimensional gradient flows. So I'm gonna talk about a u that's not a u as a function of x, but that's a just a vector. And I'm gonna talk about a right-hand side term, which is minus the gradient of a function. So this is a scalar function. Say you had two components, u and v, right? So this would be a phi, would be a function of u and v. Its gradient would be a vector with two components, d phi du, d phi dv, right? And that would give you a vector right-hand side to an ordinary differential equation. So then I'll say if u solves, u dot is f of u. This is the uxx minus f of u of the infinite dimensional Allen-Cahn case, right? If u solves this, then I can look at this quantity phi, the scalar function, which is like an energy if you want, right? So it's a scalar quantity that I can look at the trajectories, see how it behaves. I just do some chain rule to get that this is the gradient of phi dot du dt, which is the gradient of phi dotted with the f of u, which is minus that. So with the minus grad phi, and so this is minus grad phi squared. And so now you can see for such a system, phi of u of t decreases. And if you happen to have some properties of phi, like if it was convex with the minimum, then you would know that all trajectories have to tend to that minimum location as t goes to infinity. This is our Allen-Cahn energy is not quite convex, right? Because like, look, this is definitely not a convex function, even this energy part. That's why you don't have a unique minimum, right? Okay, you have two minimums, right? You could go to all -1 or all +1. Having written that, I guess I can say that this kind of thing is something that's often done in PDE analysis, is the use of these kind of estimates, which are all called energy estimates, even if they don't represent physical energy. there's a whole list, 4 or 5 examples of energy estimates in the notes. Let me just do one. So other examples of, I'll say, energy estimates are in the notes. I'll just do one. Let's look at our old friend, the heat equation. And this is with homogeneous Dirichlet or Neumann conditions on a finite interval. So really our old friend, you know, sine series, cosine series, heat equation. So we have one a priori estimate of the solution. That was the maximum principle. But there's a whole sequence of things that you can get. There's another one in the notes, but I'm going to look at one that you can get by looking at this equation by multiplying by u and integrating. So here I'm going to have u ut, and here I'm going to have uxx, right? And this term I'm just going to rewrite as this is the time derivative of u squared dx, right? Typically you would start with this and go the other way, so this is a bit of an inverse step. But if you had this quantity, then you would take the partial derivative with respect to t inside, and then you would get 2u ut, okay, and then you can see that those two things are the same. This one I'm going to integrate by parts and use the homogeneous boundary conditions to show that there's no boundary terms. And so now I know that the integral from 0 to 1 of u squared x of t dx, this is decreasing in time. So as well as a maximum principle, I know that this quantity is also smaller than the quantity at time 0. And I have to say this thing, this is not a physical energy, which you have in this problem, right? If you think of the thermal energy, it's proportional to the integral of u, and that should be conserved for Neumann boundary conditions, the insulating ones, and it is. And it's not conserved if you've got homogeneous Dirichlet conditions, but you can still make sense of energy conservation in the sense that the amount of thermal energy is in the system will be determined by the flux that comes in from the two ends. So this is not a physical energy. It's hard to say what this is for a thermal system, but mathematically it's something that is called an energy estimate anyway. That quantity is decreasing in time at this particular rate, and importantly, it's a quantity that's smaller at later time than it is at initial time. So that gives you some idea of continuity of solutions and their dependence on initial conditions in this kind of norm. And like I said, there's a number of other examples in the notes of energy estimates. And if you go on to a more theoretical PDE class, that's that's something that you will see a lot more of. I did have some computations I could show about the Allen-Cahn equations in 1 and 2D. Not sure how interesting they are, and I'm not going to get through them in the next 3 minutes. So I suggest we end here. We have one more lecture. That's this coming Thursday. It'll be another reaction diffusion lecture, and it will be about Turing instability, which is a more general idea, but one which comes up in reaction diffusion equations and is believed to be responsible for pattern formation in biological systems. So I thought that was an interesting last thing to talk about reaction diffusion problems. So we'll do that on Thursday, and then next Tuesday we officially have a lecture, but I think we've earned ourselves a day off, so we'll stop. Normally, if there was a written final exam, I would have a review lecture, but so we don't have a need for that. Okay, so I will stop here and stay on as usual to answer any questions for however long you've got questions.